Hello everyone, let's get it going. So today, we're going to be talking about classes more, right? And I might do a little bit of theory, little bit of theory about objects, but really, mostly classes. I guess in terms of announcements, let's see what we have. Let's see. There we are. Yeah, in terms of announcements, I guess the thing is that Homework 6 is this week. And then what's going to happen next week is we'll have Project 2 release, and we'll have the second midterm. And just remember that they overlap. The first week of Project 2 is the week of the exam. Now, during a regular semester, this is not so much of a problem because you'll do the project. Not quite at the same time as the exam, and you'll do the exam in class, right? So usually exam is in class, project is, on GL. So you're basically doing them in two different spots, but here everything is kind of online, so of course it's going to seem like that. So what I'm thinking of is, here's my thoughts. Maybe I can write some of the exam questions to be project related. So maybe I can write an exam question where you will either think about or do something very similar to the project, or you'll do actual work on the project. That way you'll get 10 points for a programming question on the exam, but then you can either use or modify that question, and you will have made some progress on the project. So that's kind of my thinking, is maybe we can kind of do some maybe cross-related relevant thing. Maybe I'm thinking at this point, maybe if we have 5 programming questions as usual, then maybe, and of course we're going to have something like 13 MCQ, but not caring so much about the MCQ right now. The 5 programming questions, maybe 2 of them will be project related. So in that sense, what we will actually be doing is we'll be forcing you to start early and make progress on, a part of the project. And so that's my thinking. And when I say that's my thinking, I always mean that I could change my mind randomly, and it could just be 5 programming questions, and it could be blah, blah, blah. But I will try to make it more relevant. I will try to have it so that I know that the only reason why I'm doing this is mainly because if we had an extra week in the semester, I would not even be doing this. We would have the Project 2, and then you would have your second midterm, and then you'd have Project 3, right? And nothing would ever overlap. But unfortunately, we are just like, it would be nice if the semester were like 15 weeks, but it's really 14 weeks, and so that's the way the cookie crumbles, right? As very few people say anymore. So that's the whole reason that we're doing this, is just because, if we had infinite time, we would never do this. So Project 3 is going to, what I usually do for Project 3, we'll have to see exactly what we're going to do. So I will say, so Project 3 will be, let's look at the calendar. So here we have, let's see, Project 2 is due, the second midterm is due, and then, so we're going to actually push a lot of this back. So this is not going to be our first searching and sorting lecture. Probably tomorrow is, or Wednesday. Tomorrow relative to the class, I guess. We'll push asymptotic analysis back. The special topics are fun little topics. Project 3 is assigned, Project 3 due. The issue is that we generally have to have all of our grading done within days. Unlike, it's an even faster grading process for the end of the semester in the spring than it is in the fall. In the fall, they give us the whole Christmas break up until sometime in January, like the first few days of January. So we have like 2 to 3 weeks to get all the grading done. And of course, none of this really matters from the student's perspective, but this is why everything is kind of structured. Yeah, exactly. It definitely is a TA speed run in the spring, and there's not, unfortunately, a lot that I can do about that. I do apologize to the TAs for this, but basically the reason why I'm saying that is normally what I do is I give like extensions on the project and I let you work on it during the final exam week. I am not sure that I'm going to do that this semester. I think probably what I'm going to have to do is just stick pretty hard to these due dates. And the reason why is not because I want to punish anyone. The reason why is because if I don't do that, then we won't get your grades in. So I think these are probably the due dates that we're gonna have to stick to. So as I say with like final exam stuff, it's very unlikely that you're gonna get any extensions on either Project 3 or the final, just because I imagine that if this is whenever the last day of the finals are like, we might have to submit our grades by like the 26th or something like that, and so it could be extraordinarily quick. So it'd be over the 21st, and that'd have the weekend and maybe a few extra days. And to grade 2 things, is the final structured like the midterms? All the exams are essentially identical in the course, right? So the final is basically like the midterms, basically like all the other exams. So, yep. So Project 3 will be by itself, and then you'll have the final, which is during finals week. Wow. Sometimes I give more questions on the final, like I'll give like 8 questions rather than 5, but we'll see. And I mean, since I think that next semester we're going back to in-person, it's, yep, finals are just like midterms. It's a multiple choice and a coding port. Yep, so that's basically the plan for the rest of the semester, is just, and the only thing I do feel a little bit bad about is the overlap in the Project 2 and the second midterm, but as I say, nothing can really be done about that at this point, unless we want to just continue the course into the summer, if everybody is interested in that. Okay, so I am going to begin today on classes. So remember, let's get back to the actual material for the course. So, what are classes? And so I think the way to describe them, I kind of like this. I kind of made it up last time, but it's a good way to describe it. You have types like int, you have string, you have lists, you have dictionaries, etc. When you type the word class, what you're doing is you're making a new type that you get to name, and you get to define like how it functions. Okay, so that's the idea, and so that's kind of like the idea behind a class. Basically, you're making a new thing that's like an integer, like a Boolean, string, list, dictionary. And so the 2 parts that you generally have in a class, so classes are made of 2 parts. The first part are member functions. Sometimes they're in Java and other programming languages, they're called methods. I'm not very strict about what you call them. I don't care if you call them functions, I don't care if you call them methods, I don't care if you call them member functions. I don't care about the terminology. The point is that a class can have a function inside of it, and the second thing that it has are instance variables. And I don't want to talk about the third thing because I said there's 2 things, so there is a slightly thirdish thing, but we'll talk about them. where each instance of the class has its own internal variables. So basically, let's go through. Let's just look and see. Let's see, where it is. Here it is. Okay. Is this, what is this? Okay, let's make a new file. Let's make a new classes day 2. There we go. So now let's think about what kind of things we can make out of class. So, good question. Yeah, we had the lion code. Let's make a new class though. So, I think the one that I picked for the homework was this zoo thing, right? I think that's the thing that I made the homework. So maybe we'll talk about something else. Let's see. Homework 6. Oh, Sean, our head TA, added this part here. I think our debate was on whether or not it's large enough to be visible, and my hope is that it is. So basically the 4 parts here, problem 1, 2, 3, and 4, that require recursion. The secret answer is if you don't use recursion, you're probably not going to get the right answer. But if you do not use recursion, then we are threatening you with a 0 on that part. So please, if it says use recursion, right? Recursive function, recursive function, recursive function, recursive function. Note that this one says you're making a class, right? So no recursion here, right? This problem does not require recursion. Yeah, so the debate was whether or not it was large enough to be visible, and I think that it is. So that's my hope. Okay, anyway, so we did the zoo one. Alright, so let's do a different example, right? Let's think of a new example. So what kind of things can we make into classes? So, good question. I mean, the Apple thing is an okay one, I guess. But that's all done up for the homework. So you can use classes here. Oh, no, I'm listening to you. Star Trek ships. Sure. I mean, we could do that. That's not a bad one. Let's do Star Trek first, because I love Star Trek so much. Let's call it class Starship. Alright? And, so remember, so what am I doing here? So this thing is a constructor. Okay? And so your question should be, what is a constructor? The answer is, whenever you create a new class, or I should say a new instance of a class, this is the function that runs. And so basically, what do you do in this function? And the answer is that you set up the class and get it ready to be useful, right? And what I mean by that is that you want to have all the variables. You want to have all the variables defined in here mostly. I mean, you can define. Okay, well, I'll go over that later. So, what kind of things does a Starfleet ship have? So, basically, I guess they have a name. And let's just have name here. They have, yeah, that's exactly right. You initialize, I mean, init means initialize or whatever. When I say member variables, I mean instance variable. And then maybe the hull number, right? I know that, yeah, and then maybe crew size, maybe captain and crew size, right? So you kind of have to think about all the different things, right, which a Starship can have. So let's say this is equal to name, self.whole number is equal to whole number. And so this is kind of a standard Python thing that you're going to see a lot. Right, and so, yeah, the crew could be a list of people, right? So that, self.crew is just going to be initialized to empty list. We could actually get rid of this. And so, yeah, okay, so this is a decent constructor. So the one thing, let me think. Is this good? Yeah, I think this is good. So now let's say add crew member, right? That's a pretty good function. And so what we're going to do here is we'll say a crew member, right? And when we add the new crew member, we'll add it to the crew. So we'll do self.crew.append, and then we'll append the crew member. Now you might actually want to check to see if crew member is not in self.crew. So you're not adding them twice. Then you can append them again, something like that. Else maybe you print out, hey, that person is already aboard. Something like this. Yeah, so this is all the constructor, right? This is all the constructor. This is a member function, right? So, this is a member function. It only runs when the user of the class calls it directly, or I guess technically when we call it. So what I mean by that is that if we have, say, if name equals main here, and we do something like enterprise D equals Starship, right? The name is enterprise D, and the hull number was 1701, and the crew size is 1014. So this is an example where we're creating a new Starship. We're going to call it Enterprise D, and oh yeah, what does self do? That's not a bad question. Yeah, so I'll answer it more generally. Yeah, self is a reference to the class itself. So for instance, I guess what do I mean by that? The question is, if you're inside of this function, right? Can I create a new variable called crew? The answer is I can. But this one is a local variable, which means it only lives as long as this function is running, not as long as the class is alive. And so you see the problem with this, right? Because if we said, what we're going to do is instead of doing self.crew, we'll just do crew.append. And then here what we'll do, let's say display crew, right? And then we try to get to the crew without using self. We just say print, or I guess maybe for crew member in crew, print crew member. So you see that PyCharm itself is not... so the first thing we're going to do, I guess, is we will... maybe we'll do enterprise D dot add crew member, say add Picard. Now that we're not making these classes, we're Picard, Riker, Troy, Data, Geordi. I think is that how you spell it? I think it was with a G. And Worf, obviously, etc. Right? So we're adding a bunch of crew members, right? And now here's the thing. I know that it's underlined in red, but let's pretend that we don't know that, and we try to run this function. What we're going to see is if we say display crew, and then we run this thing, what's going to happen is it's going to yell at us. It's going to say name error. Crew is not defined. And so you see that here, it doesn't know what this crew is. And so you're like, well, why doesn't it know? Because I declared a crew right here, so it should know what crew is. And you notice that here I'm kind of cheating by using crew equals empty list, and then I append it here. So what if I don't do this, right? And what if I say instead, let's actually do it the right way, self.crew, and let's put a self.crew on this. And now let's try it again. Okay, there we go. So we see here that the self, what it did was it basically changed what we call as scope. So instead of looking at the scope for the local function, right? You have the function here that doesn't actually have any variables in it, right? Crew member, I guess, is kind of a local variable, but it's just inside of this for loop. It doesn't really have any local variables other than self. Self, as it turns out, is a reference back to the original class. And so what I mean by that is, I think I said this last time, but the way that this Python does this stuff is that when we call enterprise.displayCrew, what it's actually doing, and this is weird, is this is not exactly what most other programming languages do, but this is what Python does. What it does is it calls Starship.displayCrew, and then it does enterprise D, right? So the first argument, how are user-defined classes different than dictionaries? So a dictionary is something where you have keys and values. Here, we have a whole bunch of different variables inside of this one object, right? So you can actually do something like print enterprise D dot ship name, right? If enterprise D were a dictionary, what you would have to do is you would have to do something like ship name, and then you would have to say something like enterprise D, and then you would have to say, you know, hull number, and then you might say 1701, and then you might say crew size, and then you might say something like 1014, right? So this is what member functions are called methods. Yes, that's true. I mean, as I said, you know, a few minutes ago, I don't care what you call them. You can call them member functions, you can call them methods, you can call them just regular functions, it doesn't matter. But this is the difference, right? Because here, if I tried to do something like enterprise as a dictionary.shipName, and I printed this out, I think this would give me a name error, maybe an attribute error. Let's see what this does. Attribute error. Dictionary object has no attribute ship name. So you can't do this, right? What you could do is something like this, where you said ship name like this and use the brackets, right? This would be fine. But you can't, so you can do this, cannot do this. And by this I mean dot ship name. And then, okay. And let's just put this all in if false so it doesn't run. Okay, so the point is that that's how you would do the enterprise as a dictionary. So you can access the enterprise d.shipName directly. And so you see that you're taking the class and then use the dot to access all of its instance variables, right? The dot says, I want to look inside of this object for a variable with this name. Here, when you're doing something as a dictionary, you have to access it as a key. So that's the main difference. I mean, if you ask me the question, like, is there an actual difference on the inside of it, blah, 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 how the variables are stored, that's kind of philosophy that I don't want to get into. But the answer is that there are differences between just a regular dictionary and making a class. The other thing, the other primary difference between making a class and having a dictionary is clearly here that as a dictionary, we don't have member functions, right? We're not adding functionality to the dictionary. We're just accessing variables or setting variables. So, but the only reason why I'm spending so long on this question is it's actually a good thing to think about, because it's important to know what the differences are between like a dictionary and a class, because they kind of are similar in that classes and dictionaries both store variables in a way under different names, but a class can store variables, but it also has member functions. And so as I say here, when you do say enterprise d.add crew member, what this is actually translating to in Python is Starship dot add crew member, and then it feeds in enterprise d as the first argument, and then Picard. So that's why here we also have to put a self in here as the first argument, because now every time we hit self dot, what that's doing is it's doing enterprise d dot crew, enterprise d dot, ship name, enterprise d dot whatever. And so now if we created another ship, let's create another ship. What's another good Star Trek ship? I guess Voyager. Oh God, I'm gonna start a war here. But Voyager is equal to Starship of, and then Voyager, and that'll be NCC what? I think it's 74656, and the crew size was 152 at some point. So, but anyway, so we can add crew. So add crew member, Janeway, and then let's right, block, Harry, him. I don't know why he gets his first name. No one else gets a first name. 7 of 9. Is that a first name or a last name? Hard to say. Felix. Sure. Okay, so that's the crew of Voyager. Everybody else is I guess I'm forgetting Belana Torres and a whole bunch of other people. But the point is not that. The point is I just randomly picked some people and threw them on the list. So they are the crew of the Voyager. So now what we can do is we can say Voyager, right? Dot display crew. And so we can print out, well, actually, no, I'm stupid. That's what is doing the printing out. But what I wanted to say was that when you run this, it's going to do Starship dot display crew, and then you see the problem, right? Now that we have two starships, we have the Enterprise D and we have the Voyager, which one are we referring to, right? And that's the problem. That's the problem. Enterprise D or Voyager. And the answer is pretty obvious to us because it says Voyager dot, but the point is that well, maybe I should put some hyphens then. So it's like a hyphenated identifier. Yeah, I don't know. Point is that which one are we referring to? In Python, we know because we typed in Voyager.displayCrew, but Python needs to know when it does this weird thing, weird translation. And so what it's going to do is it's going to, instead of just doing Starship.displayCrew, it's going to pass in the Voyager name into it so that Voyager then becomes self, right? So the first time we run this function, Enterprise D is self. Yes, 709, I like that. So Enterprise D is self here, right? And then here, Voyager is self, right? Wow, that's correct. That's correct. Yeah. She always liked to explain that she was a tertiary adjunct. Of course, I'm not 100% sure what a tertiary adjunct is. I guess they assist the secondary adjunct. But anyway, okay, so let's make another starship, right? So let's do the original series Enterprise, right? Because, I don't know. And so this is just Enterprise. Hull number was 1701. Crew size, I guess it was around 400. I forget exactly. And so now we got to add some crew to it. And then maybe we'll add some more member functions and do other things with it, right? Add crew member. We got to do Kirk. I guess Kirk, Spock, McCoy, right? And Spock's with a C. McCoy. Who else? Oh, Scotty. So there's a cool story about Scotty, which I don't know if I'll tell. So, let's see, what else? Who else? And then there's Sulu, who still runs his little Facebook thing, and Chekhov. I think... Now I forget if Chekhov is spelled with a K. Oh yeah, Hurrah. Can't believe. I think that's how you spell a Hurrah. I think that's how you spell it. Right? So... And then, of course, there was the first officer who eventually became Nurse Chapel. So never forget Nurse Chapel. So, okay, now that we have the crew added to the ship, now we can also display them, right? Display crew. Cool. So let's do this. And so now we see that we just listed a whole bunch of different Star Trek characters. All right, cool. So you see, I think what are we learning here? So let's get back to actually learning. So the things that we've learned are that we can make new variables inside of a class. This is kind of a Pythonic standard. I was going to say it, but then I forgot to say it. So note here, there are 2 variables in this line, right? One is called hull number, right? That's a parameter of the function init, right? Not a member variable of the class, right? The other one is self.hullNumber. And of course you might think like, oh no, this is starting to get confusing, but just go with it for just a second. The other one is self.hullNumber, which is the member variable. So basically the thing to remember is that whenever you need to save a variable for as long as the class is alive, for as long as the class is alive, make sure you do self.whatever equals something, right? That's what you need. If you're happy that this is just a local variable, if you never need it again, then that's fine if you just forget it. But if you need it ever again, then you need to remember it, and you remember it by doing self.hullNumber. And okay, and then same with crew size. The other thing I think we're learning is you can make lists and even dictionaries as member variables. So technically, you can even have a class as a member variable, right? So technically, I don't know. Let's make a new class called Warp Drive, right? And this is going to be a pretty basic class, kind of like a subclass. I don't want to use the term subclass because that might hint at inheritance or something like that. Lots of things are confusing, but we do them anyway. So let's make a class. Let's say that max speed. What else? Per second, I don't know. And so basically we're going to have a class of warp drive, and so we'll just have max speed equals max speed, and then self.dilithium per second, DPS equals dilithium per second. Okay, there we go. Cool. Oh yeah. Self.singularity equals false. So because remember, and this is very important, the Romulans used quantum singularities, many black holes, somehow, for their drives. Point is that none of that really matters. The whole point is I just wanted to make a new class, right? You don't have to be extraordinarily we're not learning anything new here, right? Nothing new is being learned about the creation of the warp drive class. The only reason why we create it is so that we can do here is we can say def set engine, right? And this will be warp engine. And so what we'll do is we'll say self.warp engine is equal to warp engine, like this. And so, okay, so let's do this. So let's think. Warp engine, warp drive, oops. So the max speed for the Enterprise A, I forget, they did a different rating on warp speed, so let's just call it 8.0. Dilithium per second, 0.1234, because who cares? That's not even a number that exists, and singularity is false. So original Enterprise drive equals this. And so what we can do is we can go original Enterprise dot set engine, and we can do this. Are there never spaces around qualities and parameters? Oh, good question. In terms of your coding standard for the class, I don't care. But in terms of for default parameters, and remember that this is a default parameter. So what that means is that if you don't include it, like if you notice here, I haven't included it, it's going to be whatever it is in here. So it sets itself to false if you don't include it, right? And then, of course, the spaces business, the spaces, it says, the PEP8 standard says no spaces between the variable equals default. But for this class, who cares, right? Oops. Right, we're not, I promise you that the TAs are not, like, at least the vast majority of them are not experts on the PEP8 standard, and they are not going to penalize you for, like, doing this instead. You notice that if you do this, then PyCharm is going to say, don't do that. But it's just PEP8 rules that you can either follow or break. So anyway, so cool, right? No, Sammy. I don't know why I called you Sam for a second there. All right, Sam. Sam the man. The point is that though Sammy knows all the coding standards and will punish her students severely for breaking any of them, the rest of the TAs don't care. So, okay. All right. So now we've set the drive. Here's a little bit of thing, and then let's make a new warp drive. So let's say new drive is equal to warp drive. I think the Enterprise max speed was something like 9.9, like something, 9.95. We'll just do 0.2211. And let's say false, right? So it was already set to false, but maybe you're afraid, so you'll set it to false, and then we'll set Enterprise D dot set engine to new drive, right? So that's basically the idea here. So that's the only thing that we have to be careful of, and I think this is one thing that I'm going to tell you to be careful of, is watch this. So here is a cautionary note. So you remember how I was talking about things that are mutable and things that are immutable, and we haven't really had to deal with that. You know that lists are mutable, and you know dictionaries are mutable, and you know that other things are not mutable. So the thing to remember is that classes are mutable. Therefore, and so here's the important thing, therefore, they always pass by reference into functions. And so what do I mean by that? And let me explain. So when I pass this engine in, right? And I set self.warpEngine equals warp engine. What it's actually doing is it's setting self.warpEngine equal to not just a copy. This is not a copy. This is just a renamed version of either this one or this one. So now what I'm going to do is I'm going to set Voyager dot set engine, and I'm going to set them to have the new drive as well. So they're both going to have the same drive, even though you can pull out the technical schematics and be like, hey, that's not true. And so what you say is, hey, Voyager has a faster top speed or speed or something. So you're like, oh crap, okay, so new drive dot, or even worse than that, we can do Voyager dot engine, right, or dot warp engine dot max speed, right, equals what? Let's say 9.9975. Actually, let's just look it up, because we can always just look it up in the Star Trek wiki, right? 9.975, so get rid of one of the nines. Cool, whatever. So now that I've done this, so here's the point. I'm going to print out Voyager.warpEngine.maxSpeed, and now I'm going to print out Enterprise D.warpEngine.maxSpeed, and let's see what happens. Huh. That's weird, right? Not really that weird, but maybe unexpected, right? So the what am I saying, and what is happening here, right? What's happening here is that we set the Voyager engine to this new drive. We then changed its max speed, and then we printed out its max speed. So this one you should totally believe, right? This one is totally fine, right? This one is completely believable. But what about the next one? Printing Enterprise D.warpEngine.maxSpeed. Well, when we stuck in the max speed, it was 9.95, not 9.975. So why is it the same as Voyager now? And the answer is that I fed in the same new drive into both Enterprise D and Voyager, right? These two things are the same, right? And so what happened here when we did this set engine was, remember that this passes as a reference. So it's not actually creating a copy of the variable. What it's doing is it's just saying, pretend that the variable is called warp engine for the purposes of this function, but it's not creating a copy, right? It's using the original new engine variable from down in there. It's just renaming it. And so the way to think about it is that, I think the way to think about it is this. Let me just draw a little picture. So here you have Enterprise D, and here you have Voyager, and so they both have, and so here's new engine, right, or new drive, or whatever we called it. And so the answer is they both have a variable called self.warp drive, right? So this is like Enterprise, let's say this one has warp drive, and this one has warp drive, right? So they both have variable names that are called warp drive. But actually, both of these variable names are just sort of pointing to the same new drive from the original. They don't know that the thing is called new drive. They think that it's called warp drive, right? They don't know what it's actually called. But all the data, the actual class, the information, right? So there was the original drive that's over here. And you have the original Enterprise here. Original, and I know it was original Enterprise, not that way, but I don't care. And then here we're just going to do this, and then I will probably do something like that. So you see that this is how it kind of works, is that they all have a variable called warp drive. This one is pointing to the new drive, this one's pointing to the new drive, and this one is pointing to the original drive. So you can change this one and it won't have any effect on this, but you cannot change this one without having an effect on both. The correct answer is, if you actually wanted them to have separate drives, then you have to pass in separate drives, right? So I'm just doing this intentionally to kind of show you how references work, how it works within a class, how passing things in creates either a copy, right? If it's a string, then it's a copy. If it's if it's a class or a dictionary, a list, then it creates a reference, right? And so the way to think about a reference is that there is an underlying object in memory somewhere, and it can have multiple names, right? And so those variables are all called references, right? Now the actual object is going to be called something like, list underscore blah, right? But, we call it, or I guess you might call it something like class, right? That's what Python calls it, but we never get to see that name. So Python might call it, we call it new drive and, self.warp drive, right? And it doesn't matter that it has two different names, because it's both of these names are actually looking at the same exact object in Python. Okay, so that's a good thing to explain. So now let's get away from Star Trek and let's do something else. So, sure, let's make this Star Trek. So what's another good thing that we can do that's not Star Trek? Let's make some new classes. Let's make, let me show you an example of kind of a, let's do an, okay, I have an idea. Let's do Frogger, right? So, the Frogger, the game. And so what kind of things would you do? Maybe Star Wars comes in a later example. I've done enough Trek and Star Wars, Star Trek stuff to satisfy myself for this lecture. As you can tell, I am a significant Trekkie, but that is a personal problem, really. So, for now, let's get back to Frogger. And the reason why I want to do Frogger is because it's going to remind you a little bit of the project. So, even better than Frogger, how many of you have heard of the Game of Life? Well, Crossy Road is probably like Frogger, yes. Let me remind myself of the Conway's Game of Life. So there's a set of rules to Conway's Game of Life, and oops, I'm just going to use this website because I'm too lazy to. Well, actually, no, I'm not too lazy. This is just better than anything I can come up with in 10 seconds. So here's the rules. For a space that's populated, so basically what you do is you have a grid, right? And for any space that's populated, so that means that if it's yellow, if it has one or no neighbors, then it dies. What that means is that if it's an active square, then you demote it back to being a passive square. Each square with 4 or more neighbors dies, as if by overpopulation. And then each cell with 2 or 3 neighbors survives, okay? So here's what we're going to do. We're going to make this game. I think there's time. So let's just show it how it runs, and let me just show you how it's doing. So this is how Conway's, oh, cool. So here's Conway's Game of Life. Let's see, reset, clear. Let's just make something like this. Okay, so what's going to happen here is that the next one is, you see how there were 3 here, so it filled it in. And then this one's actually stable because each one of these has 3 neighbors, so it survives. So let's add this in and see what happens next. Whoa, right? So now this one has, so now I think everything's just going to die. Yeah. But anyway, let's try to make some other shapes. Let's try to do something like this, maybe? What do you say? Something like this? So what happens now? So you see that happens, this happens. Ooh, nice. So this is kind of the unpredictability of Conway's game of life. It's pretty cool. You see how it's following all these rules, and it's doing this kind of behavior with, you know. Actually, that was a pretty good starting position because it hasn't all just died off yet. I think it's about to... Okay, well, it made a stable 4 square. Well, nope. So you see that there's actually, you know... Yeah, that's one way to describe it, as an emergent system. When people say emergent, what we usually mean is that it's like a simple set of rules that can generate complex behavior, right? That's what emergent generally... I mean, you can argue with me about the definition of emergent, but yeah. So let's make Conway's game of life, right? So this is pretty cool, right? You'd say that if we made this in 10 or 15 minutes, that would be something that would be a good example. So let's make Conway's game of life. Okay, so what are the things that we need, right? Let's say board X, board Y. Okay, so let's make a board. And unfortunately, I'm going to have to do this in a stupid way, but I don't care. So let's use booleans, right? Let's say false if the board is inactive at that position. And let's say true if it is active, right? Or alive, right? Okay. Neighbors can be diagonal in this case, so we're actually going to have to think about that. So that's going to be pretty cool. So let's make the board. So yeah, so let's make the board. The board is going to be for I in range, board X. We are going to say, and then for J in range, board Y. What we'll do is we'll say row equals empty list, row.append false. We'll just start everything out as dead. Okay, start everything out as dead. And then at the end, we'll do self.theboard.append. Let's make it an empty list to start. And .append row, and then we should be good. So that should be fine. Okay, cool. Now I'm not doing any safety checking. Let's do a populate randomly. And let's use a probability here. And so now what we're going to do is for I in range, len self.theboard. For j in range, len self.theboard, say 0. And what we'll do is we'll say if random.random, which of course I haven't imported yet, is less than probability. Technically you could do greater, but less than should make it so that the probability of life is equal to that. Then what we're going to do is we're going to set self.theboard ij equals true. Okay? So now let's import random. Let's put random up here. All right. Cool. There we go. So that'll populate it randomly. So now let's make a display function. And so, what are we doing? For I in range, len the board, self.theboard. Oh, where are my headers? Oh, I'm totally not documenting anything. Yeah, let's document some stuff. 0 is less than prob is less than 1. Should fill is the probability that we will fill in a space with a live entity. The rest are sent to dead. And then return nothing sets self.theboard. There we go. Well, the rule in life is that you have to do as I say, not as I do, right? Unfortunately, that's the rule of all teaching. But sure, let's document this class. You can delete the return. You can just say displays the board contained in self.board. Okay. So now let's display it. So let's do self.theboard, say I, and we'll have to do, say, maybe dip.join. Oh, crap. I'm using... let's change it from true and false to X and space. That way it'll be easier to print. Okay? So we can even create some constants here. So we'll call it self.dead, and we'll call this self.alive, just in case we want to change them in the future. So you can say self.dead is equal to an empty space, and self.alive is equal to an X. Cool. All right, there we go. Now this should work. And then we will print out this, and then we should be good. That should be it. All right. So this one is going to be the actual worker function here. So what this is going to do, you can, but you can't join them, right? I just wanted to use join. You can print Boolean values, but you can't join them. So remember, I want to get this done by the end of lecture, so I'm trying to be lazy here. So yes, constants for the classes can be defined inside of the class in the init, or even worse, what you can do is you can even do this: dead equals space and alive equals X, like this. So, and I haven't described what this is yet. I'll probably talk about this next time. So this is where you can put constants. Yeah, Sammy's right as well. So it'll kind of mess up our grid. So I'm just kind of trying to make it more watchable, lookable. Okay, so remember what the rules are. So let's remember the rules. If at any space the number of adjacents is 0, 1, or what is it? Bigger than 3, then we set it to dead. And then else alive. Okay? So what we have to do is we have to go through the board. So let's do this. For I in range, actually, here we go. Stolen. Let's make a helper function, right? Self.set dead or alive ij. So that's going to make this function much more beautiful. So now what we're going to do is set dead or alive, and we'll just call this xy. And now what we have to do is we have to look at all the spaces that are around it, right? So we have to look at for I in range, and so actually no, I'm going to even do it differently. So instead of using a range, what I'm going to do is I'm going to say for I in -1, 0, and 1. For j in -1, 0, and 1. Okay? So this is what I'm going to do, and maybe you'll like this or hate this. So it's going to look through all the different possibilities, and this is, let's call this x offset, and let's call this y offset. Okay? So what I'm about to do here, I don't want to do recursion. Not for this. So recursion is good. This shouldn't be done recursively. That would scare me. So what I want to do here is I want to say num adjacent equals 0, and then I say if self.alive is equal to self.board at, and then this is what we're going to have to do, x plus x offset and y plus y offset, right? This will push us, this will be where we are, and this is how we go around it, right? Oh, classes can definitely have recursive methods. I just don't want to do it here. Num adjacent plus equals 1. And then, and so there's some problems with this that we're going to have to deal with, but we'll deal with it in just a second. So then we say if num adjacent is in, say, well, I guess really the only things that it can't be are what? If it's 0 or 1 or bigger than 3, we set it to dead. So if it's in 2 or 3, then we do self.theboard xy equals self.alive. Else, we set it to dead. Like this. Okay, cool. So that's done. But now we have to ask ourselves, what are all the problems? Right? What are all the problems with this? So there's two problems with it as written. One problem is that because we're adding to offsets, right? Because we're adding to offsets, if we're at the edge, we might go over the board. So we don't want to go over, right? We don't want to go overboard. So what we have to do is make sure that if 0 is less than or equal to x plus x offset is less than the length of self.theboard. And also 0 less than or equal to y plus y offset is less than length of self.theboard 0. And so what this does is it makes sure that we're in bounds, right? This, before we execute the checking, we want to make sure that we're in bounds, because if we're not in bounds, we don't want to be adding to any of the adjacents. We don't want to be doing that, otherwise we're going to get index errors. Okay. So, yes. Okay, so now that we fixed that problem, there's actually still one slight problem left. And that problem is what happens when x offset is 0 and y offset is 0. The answer is that we're actually just looking at the position xy, which is not looking at the adjacents. It's looking at the center position where we are, which doesn't get counted, right? It should not get counted. So basically we should also say, right, maybe if this is the case and x, and maybe not, x equals y equals 0, right? So that'll fix that one. So the other condition is if x offset and y offset are both 0, then we're not looking at an adjacent square. We would have been looking at the square itself. The square itself. So check for that. And so I think at this point we're done. I think we've coded the game. Well, I shouldn't call it a game. It's a game for the little creatures. It's not really a game for us. It's just something for us to watch. So let's do a, let's see, Conway Game of Life. Let's make it a 10 by 10, right? And so now what we're going to do is we'll say while s not equal to quit, right? So we'll make s equals to input. Sorry, I'm doing all these typos. Let's continue or quit. And so we'll do s.lower like this. And then if this is the case, then what we'll just do cgl.step and cgl.display board like this. So we'll display the board once, regardless. Populate randomly, input, float, or no, crap, float input, enter the probability for filling. And so there we go. Okay, cool. So I think we should be good at this point. We'll populate, then we'll display, and then we will do two things. We'll step display, and then we'll input at every step, because if we don't, then it's an infinite loop. Yeah, it's an infinite loop. Wait for what? What am I doing? What's happened? I have to update? Yeah, that's what step is. Right? So that's gonna step every time. No, you're good. You're good. Yeah. So that's. I think we're good. I'm gonna click run because I don't know. Yeah, and as you notice, what have I not done? I haven't tested a single thing. So this is definitely gonna work, right? I mean, 100%. This is gonna work. Let's make the probability 0.05. All right. Well, that didn't fail. Yeah, so let's run it. Let's say C for continue. Whoa. Is that right? So... I don't think that can possibly be right. But let's see what happens at the next step. Okay. This looks like it's not doing correctly. I could be wrong. Yeah, there's some weirdness going on here, right? There's definitely some weirdness going on. Interesting. I'm just curious if, I mean, is this right? I mean, I guess the one thing to say is that it looks like this is actually stable at this point. This one should be dead. This one should die. Right? So... yeah, let's look at our... so our step function is right. It goes through the whole board, so this is fine. The issue here is... let's check the rules for Conway's Game of Life again, just to make sure I'm getting it right. So the rules are... if it has fewer than 2 live neighbors, it dies. If it has 2 or 3 live neighbors, then it goes on to the next generation. With more than 3, it dies. Any dead cell with exactly... oh, I see. So I'm not actually... I'm sorry, I'm not actually following the rules exactly. So, okay. If the thing is alive, then we keep it alive. So if the number of adjacent, basically this, if the number of adjacent is equal to 2 or 3, and the thing is alive, right, then it stays alive. And else it becomes dead, right? So the rule is that any live cell with 2 or 3 neighbors survives. Any dead cell with 3 neighbors becomes a live cell. So if the number adjacent, right? Let's say if the number of adjacent is equal to 2 and self.alive. Else if the number of adjacent is equal to 3, and then it doesn't matter if it's dead or alive. If it's alive, it stays alive. If it's dead, it becomes alive. And then the last rule is that all other live cells die. So so let's see if this makes a difference and changes the way that the game operates. Because we've fixed... so this is not actually this wasn't really a coding error. This was just me not reading the rules carefully enough. So it was actually what we would call a logic error. It was an error in, let's say the probability is 0.02. Okay, so if we continue here, everything should die. Yes, good. See, now that worked. right? Because if we look at it and we say, what should happen here? The answer is this guy has no neighbors, this guy has no neighbors, so they should all die. Okay. Now let's increase the probability. Let's say that the probability for filling is like, say 0.5, so 50%. So now we have a very full thing. So let's continue a few times. So the first thing that should happen, right, is this one should definitely die. This one has 2 adjacent, so it should live. This one has 3 adjacent, so it should live. This one has 1, 2, 3 adjacent. So a lot of these should survive. So we should not just go to a completely dead state. So let's see what happens. Okay. So as you see, this one did die because it had no neighbor here, and no neighbor down. So that's good. So that's correct. These all survived. Or, no. This is a different shape now. So let's see here. It's kind of hard to see what's going on. So this one is alive because this. So should this one be alive? Yes, it had 3 neighbors before, so it should be alive. What about this one? Should this one have died? The answer is it had 3 adjacents, right? 1, 2, 3. So I think, right? So it shouldn't have died. This one is adjacent, this one, and this one. So this one. Good point. Good point. Might make a smaller grid easier for testing. So let's make a 5x5 grid. And let's make it 0.5. Cool. And let's continue and see what happens. Actually, what we can also do here is fill this in on a real grid and see what happens. But anyway, so yeah, so should this one have survived? This one has, in the previous step, it had only 1 neighbor, so it should have died, but it lived. Interesting. Why is it should have died, but it lived? So what's wrong with the code? If the number adjacent is equal to 2 in this. Oh, I'm an idiot. Wow, okay, I'm sorry. This is bad. This is extraordinarily bad. Let's think about why this is bad, and then if x offset equals 0 and y offset equals 0, right? We actually want this. So or we could use De Morgan's on it. So x offset not equal to 0 or y offset not equal to 0. There we go. That should fix this. I think at this point maybe we'll see. You're right. So let's say 0.5. Let's see what happens if we continue. So now let's see what happens. So these both only had because if they're both equal to 0, we don't want to add. So this one only had 1 neighbor, so it should die. This one had 2 neighbors, so it should have survived. Right? What else happened here? This one had 1, 2, 3, 4 neighbors, so it should have died, and it did. This one had 4 neighbors, so it should have died, and it did. This one had 1, 2, 3. This bottom one had, what is it? 1, 2, 3, 4 neighbors, so it should have died, and it didn't. This one had 1, 2, 3, 4 neighbors, so it should have died, but it didn't. Interesting. Interesting. What do you mean looping? Oh, yeah. So what we actually want to do... Ah, oh, man, you're right. You're right. That's absolutely true. That's right. Yes. So you have to do this all generation by generation. So we can't actually do this all as one thing. So we're going to have to do some... We're going to actually have to do a bit of additional trickery. So here's what we're going to do. And this should actually fix everything. So this should fix it. We have to create a new board. And so we'll call it new row equals this. And then we'll do new row dot append this. And then what we'll do is we'll say new board dot append new row. And then finally, at the very end of this, what we're going to do is we're going to say self dot the board equals new board. So that'll fix that part. And then what we have to do here, instead of setting the... What we'll do here is we'll just return alive, dead. And so that will fill in the new board, and then we will reset the board to be the new board and forget about the old one. So let's see if that makes a difference, right? Let's see if that fixes it. So let's say 0.25, so there we go. Let's continue. So this one has 3 spaces, so it should exist. This one has 3 spaces. This one has 3. So that's why we're getting these coming into existence. This one has 1, 2, 3 neighbors, so it should be fine. This one has 1, 2 neighbors, so it should live. This one has 1, 2, 3 neighbors, so it should live. This one has 3 neighbors, so it should come into existence. So that's right. This one has 1, 2, 3 neighbors, so it should come into existence. I think this is working now. Oh yeah, look at that. This is starting to look like... Yeah, this is definitely starting to look like Conway. I mean, of course, this is not a completely holistic test, but I think that this is definitely... Yeah, this is definitely starting to look more like Conway. Nice. And that's great, because that's the end of the class. The good news is that we fixed everything. Yeah, thanks, Sammy. I really... I did not... I didn't think about that until you pointed it out, and then I was like, oh my god. I cannot believe what I was doing. Yeah, so basically... You know, hey, but I did actually finish it sort of within the class period, so that's good, right? Yeah, see, and maybe you'll think about why Sammy was right and I was wrong, right? Let me just tell you why, right? In a more kind of coherent way. The answer is because what was happening is the board was remembering its previous state while it was also getting set to new values, right? So the thing is that it was looking around itself, and if we took away a square, then it wouldn't have counted that. And then if we added a new one, it also would have counted that. And so the point is, in Conway's game of life, everything, you turn the crank all at once, right? So you turn the crank all at once, and so that's why you have to do this. Yeah. So in your project, in the Battleship project, you won't have to do the new board business, mainly because you're only going to be firing one shot at a time and stuff like that. So you're not going to have to worry quite so much about this. This was mainly just because I was doing this too quickly and didn't think about it hard enough. But hey, I mean, you know. Anyway, so you can see how you can kind of make something like this happen, you know, within what? About 15 minutes. I think it took me about 15-20 minutes. So, okay, so I think this is a good example. I think one reason why this is such a great example is because it's like a complete game. It's like done, right? right? So that's one cool thing about it, is that it's kind of it's like a self-encapsulated thing that you can actually look at. Maybe I'll tell you what, maybe I'll even put it in a separate file. Maybe we'll do Frogger next time or something like that. So, Conway, game of life. And so you can kind of use this as an example when we get to project 2, okay? So, okay. All right, so I'll post this stuff, and I think that's it for today, right? That's all I got. And Conway, and second day of classes. And let me commit, and then that'll be the end of the lecture. Well, I committed already. Let me push, and then we'll end. All right, I think that's pretty good, right? We made Conway's Game of Life. And we did a little Star Trek stuff. So I know that we only did 2 examples today, but I think we spent time on them, right? We really fleshed them out. So there's a lot of, it's not quite a project, right? This whole thing, this is like half of a project, but we did it in 20 minutes, so not bad, not bad. Okay. All right, I'll let everybody go. Thanks for watching. Thanks for attending lecture and all that. Let me go and do the outro.